In this lesson, we are going to talk about mainly inheritance. So in Python, there are multiple and single inheritance. So Python supports multiple inheritance. It means that it can inherit from more than one class, but multiple inheritance can be a little bit tricky. So we are going first to study single inheritance, which means that we are going to inherit from a single class. We're going to explore the single inheritance chain. And the one important note that I have already made, so technically all classes inherit from the object class. So let's understand the fundamental concept behind the inheritance. So let's say we have an abstract class, shape. So we are going to inherit from the shape and create instances of this shape class. So we're going to create a polygon, we're going to inherit from shape, we're going to inherit from shape, we're going to create a line class, and we're going to create ellipse. So we're also going to say that in the polygon we will have triangle, rectangle, and etc. And for an example of ellipse, we're going to create class circle. So we need to first understand the terminology behind this. So first we have the parent class, which is, for example, can be a person, which has a name, for example, it has a method, it, for example, and we have the children. We have the teacher, which is inheriting from the parent, and we have student, which is also inheriting from the parent. So they are both children of person. So teacher has the method, for example, teach, and the student has the method of study. So this is an example of single inheritance. So here, student inherits from person. Student is a child of a person. So we also say that student is a subclass of a person, or student subclass is person, and we also sometimes say student extends person and student derives from person. So, but the most famous way to say is student inherits from person and student is a child of person. So let's understand that objects that are created from a class are called instances of that class, as you remember. So we have person, we have teacher, we have student. So we have P1 equals to an instance of person, S1 equals to an instance of student, and T1 equals to an instance of teacher. So S1 is an instance of student. So student inherits from person. So S1 is a person, yes. S1 is an instance of a person, and S1 is not a teacher. So these are important things that you need to remember here when looking at this hierarchy. So let's understand the difference between is instance and the type. So when we have the same hierarchy, the person and the two childs, the parent class, person and two children, teacher and student. So when we say is instance S1 student, of course it's true because S1 is an instance of student. Is instance S1 person, yes, because it's an instance of parent, also class. Person, that this is true. So is instance S1 teacher, of course it's not a teacher because it's a student. And is instance P1 student will of course returns us false because P1 is not student but a person. So for the type, the type returns the class the instance was created from. So type of S1 is student, type of T1 is teacher, and type of P1 is person. So it's more often better to use is instance rather than type, because let's say we want to call the it method of an object if it has one. For example, if type object is person, then we can call object of it. But if object is a student or teacher, this won't call the it method because we are only checking that the type of object is person. If instead we need to write for this, if type object is person, student, teacher, giving the list, then we can call object of it. It's much more simpler to say if this object is an instance of person, if it's this so incorporates both student and teacher, then the object of it method will be called. So it's far more better to use is instance rather than type. There is also a subclass function in Python object-oriented programming. So it's used to inspect inheritance relationships between classes. So we have here person, the children, teacher and student, and the student has two children, high school student, college student. So if I say is subclass student person, of course it's true. Is subclass college student, and of course it's true. And is subclass college student person, of course it's also true. So let's talk about the object class. So when we define any class in Python that does not inherit from another class explicitly, then Python makes this class inheritance from object implicitly. So object is just a class, even though it does not use any camel case, the convention of naming of the classes. So this means that every class we create is a subclass of object. So every object, even functions or objects, are a subclass of object. So here, when we have a person class, it's inherited from object. So person is a child of object actually, and then the person has children, teacher and student. So when we write is subclass student object, it will return us true. And if we say is instance s1 object, if it's again will give us true. So whenever we create any class, it automatically inherits behaviors and attributes from the object class. So the special methods name, new, init, wrapper, hash, and equal. So even if we create an empty class, class person, and we create an instance of this class, so we will have the p.wrapper, which will return us this. We will have p.hash, will return us this number, and p equals to p will return us true, which is the equality. So let's understand what does it mean to override functionality. When we inherit from another class, we inherit its attributes, including all callables for the methods. So we can choose to redefine an existing callable. So this is called overriding. So whenever we have, for example, a class person, the person is the parent class. It has two methods, say hello and say bye. Whenever we have a child of it, class student, which inherits from person, so we can override the say hello and say that say hello for the student will be return yo. So in this case, whenever I call student dot say hello, which will override the person's say hello and will return me yo. Whenever we use say hello over the person instance, it will just say hello. So overriding functionality, when we create any class, we can override any method defined in a parent class, including the inherited ones. So for example, if I say class person define init self.name equals to name, actually we're overriding the init in object class, which is the parent of this person. And when we say define wrapper self return person name equals self.name, we're overriding wrapper in object. For example, when we have the class student, which has the parent person, and we say define special method wrapper self, we're actually overriding wrapper for the parent class person. So overriding mechanism works like this. So suppose we have a type of hierarchy, we have the person, which has the methods eat, sleep, work, and routine. Now if we want to create a student class that overrides the work method only, so we can say the student has work method, which is now returning student studies. And what happens when we call the routine of a student instance, for example, when we say s equals to student and we call s.routine, so student doesn't have the method routine, but its parent, which is person, has the routine. So it will run a routine defined in a person class, but bound to s. So it will just return whatever written in the routine in the person class. So it will execute eat, work, and sleep. So it will print that person eats, that person sleeps, and then person works. So there is one important thing for delegation to a parent. So let's say we have such kind of an example where we have the class person, we have the initializer for this class defining init, which has the name and the age, and when we have this child of this class, student person, and we are saying that this initializer, besides this name and age, has also another attribute, which is self.major equals to major. But we see that when we are creating a child, we are like duplicating the code here. But so there is for sure a better way to do this. So we can easily call a method from the parent class, so which means delegation to a parent, which is using the famous Python syntax super, and we can use super.method. So we call in the method in the parent, but bound to the instance. So example of this can be, for example, we have a class person, we have the child student, and we are now saying that return super.sync, which is returning I am lumberjack and I'm okay. And then we say that use besides this add a slash and enter and say that I sleep all night and I work all day. So whenever I say s equals the student and say print s.sync, what it will do, it first go call the super.sync. Super means we are delegating to a parent, which is in this case person, so it's returning us I'm lumberjack and I'm okay, and then it adds the enter, and then I sleep all night and I work all day. Also, what we can do, the most famous way to use this super is when we use it as initializer. So we have class person, we have the initializer for the person, we have the class student, and we say that here I'm using the super of init, so we are using the parent init, giving the name and the age, and we are adding some additional thing, which is the self called major equals to major. So first we are delegating back to the parent and to work some additional work. So when delegating, you don't have to delegate first, but it's usually safer to do so. So another famous thing in Python to save memory is called slots. So whenever we have some instance attributes, they're all normally stored in a local dictionary of all class instances. So whenever we have the class point, we are defining an initializer self.x, self.y, and then we print we initialize the class instance p equals to point. We see that the p.dict has the x and the y, and then we know there is certain memory overhead with dictionary. So what we have when we have like 1,000 of instances of point, like a lot of overhead. So for that, Python introduced another thing called slots to alleviate this problem. So we can tell Python that a class will contain only certain predefined attributes. So we say that if I have a class point, it can only have x and y. So it doesn't have anything else. So when we say p equals to point 0.0, it doesn't have p.dict. It doesn't have anything. So it has just x and it has just p.y and nothing else we can define. So this is memory saving. So we can see the difference whenever we have a class point and we initialize like 10,000 instances. Here in this case, I will have like 1,729 kilobytes, and if I have the slots, I will have 635 kilograms. So this is very useful thing to use slots. So in general, using slots fastens also awesome operations on average. So let's say we have such kind of an example. So whenever we try to use this function, when we have the slots in the class, we will see that when we do the time comparison of the manipulate, dig, and manipulate slots methods, we will see that with the help of the slots, we're about 30% faster. So why not use slots every time then? So if we use slots, then we cannot add attributes to our object that are not defined in slots. So whenever we need to add something, so for example, we have the x and y, and we want to add another coordinate, for example, the z, like p.z equals to 100, and set attribute to p.z, we will get an attribute error because we define in our slots, and we only need to have for point x and y, and that's it. So this is it for this lesson.